For our last topic for the semester, I'd like to talk about some alternative sources of energy. We've talked about fossil fuels, we've talked about mining, we've talked about the challenges with waste disposal, and we've talked about climate change. And all of these things seem to tie in, I think, to one major problem, which is our dependence upon fossil fuels, things like coal, oil, natural gas. And there are lots of other resources out there, and over the last, say, decade or so, they've actually been gaining quite a bit of traction in terms of how much states and then countries too are really starting to move away from fossil fuel use and into more of the alternative energy sources. And so alternative energy here means those things that are not fossil fuels or nuclear energy. So if you look at this graphic here, what it's essentially showing is that in 2018, the 2019 data isn't really out yet. This is talking about up until April 2019. It's the preliminary data, so they're using it just for 2018. Here's the U.S. energy consumption by energy source. Notice that we are still heavily dependent, right, on fossil fuel use, at least in the US here. So petroleum being a fossil fuel, natural gas, and then coal. Now, technically too, nuclear electric power, and we'll talk about that in a minute, can potentially be considered non-renewable as well, because it actually uses the mineral uranium. And so we have a limited amount, of course, of how much uranium is on the planet. But this small section here, right, this 11%, this goes into the renewable energy or alternative energy sources. And so if you look at the breakdown over here of those renewable energies, right, those things that actually can be renewed on a timescale where they can be renewed at the same rate or even faster than the rate that we use them, those are things like geothermal energy, solar and wind, burning of biomass, and then we'll talk too today about things like hydroelectric power. So we're going to kind of leave fossil fuels because we talked about those in a previous lecture, but I want to talk today about these renewable energies as well as nuclear electric power. All of these are now considered alternative energy sources. So still, fossil fuels produce about 81% of the U.S. energy annually. Now, that was last year's numbers, so I haven't actually updated it from the previous slide. My apologies for that. It's probably a little bit lower now, but still, notice that between nuclear and alternative energies, renewable energies on the previous slide, we were only at about 19 to 20%. So this number might be still pretty similar to what we've got today, right? 81% of the U.S. energies are still being produced by fossil fuel production. So alternative energies are those things that are generally renewable, but they are essentially, so not all of them, right? Nuclear is not necessarily renewable, but they are alternative to fossil fuels. So what do I mean when I say renewable versus non-renewable? Renewable means that you can essentially replenish the source at a rate equal to or faster to its consumption, right? So we use wind energy, but we can create more wind to produce more energy in a very rapid rate. Same thing with things like solar. I mentioned wind, hydroelectric, geothermal, right? That's just heat from the earth, and biomass, right? These are all renewable alternative energies. Now, nuclear energy is an alternative energy resource, but I wonder if it's technically more considered non-renewable just because it does technically still use a material that is not currently being produced in the earth, and that's uranium. So we'll get to that in a few minutes, but let's kind of talk about some of these renewable energy resources. We'll talk about what they are first, how they produce energy, and then also the most important part is what are the pros and cons of each. The benefits of using renewable energy, of course, is that the first and foremost, right, number one, they are inexhaustible. It means that we can use as much as we want, but it still gets generated, right? So sunlight is a good example. We can use as much sunlight for solar energy as we need, but we are still going to create more solar energy, so we can keep using it. We talked a little bit too about wind, biomass, geothermal, and hydropower. All of these are inexhaustible because the wind keeps blowing, the water keeps flowing, and the earth continues to be hot if we drill down into it. So all those things are great because that means that these are inexhaustible resources for energy. Most of them are going to have a minimal environmental impact. Now, we're going to talk about some of the impacts to the environment, especially things like hydropower, and maybe some of the other ones like mining for the materials for solar photovoltaics. But essentially, they have a minimal environmental impact, especially when they are compared to things like fossil fuels. They are renewed by the sun's energy, or I should also put, energy from the earth. So if we talk about geothermal energy, right, we're talking about energy that is interior to the planet, but again, renewable, right, because the sun keeps shining and the interior of the earth stays hot. With the exception of burning of some of the waste associated with this, for example, if we did biomass energy production, there's really no fuel used, right? Like you're not actually having to use fuel, any sort of fossil fuel or otherwise, to kickstart the procedure to then make that energy. It literally is all renewable, so that the wind just blows and the windmill moves, or the sun just shines and the photovoltaic panel makes energy. You don't need to have any sort of an additional fuel source to keep this thing going. The last thing too is that it's relatively a short developmental time. So, once the planning starts and whatever else, to put in these alternative energy resources into a power grid, it's really not too difficult. In fact, many houses even now have their own solar arrays. And our very own Brian Zimmer, actually, who teaches in our department, even has his own geothermal heating system in his house. They actually were able to dig a geothermal well, and he heats his house by pumping ambient temperature water underneath all of the floors. So the graphics over here on the right essentially show that in North Carolina, these are kind of the types of power plants that are alternative energy power plants that are found kind of in the southeastern part of the U.S. Notice that there's quite a few in terms of solar, or passive solar voltaic. There's a couple of wind farms, especially down here in South Carolina. Several biomass burning locations, and as well as there's a couple of geothermal sites. If we look down at the graphic in the bottom, notice how this is in 2005 and this is in 2017. So this is the change in energy production in North Carolina from 2005 to 2017. 95% of the energy produced in North Carolina that was fossil fuel burning, right? This is essentially, so all of the fossil fuels that were used in North Carolina, 95% of them in 2005 were coal-based. So we were actually relying on energy production just in the fossil fuel sector, right, from coal. Notice how now in 2017, the amount of energy produced from coal is reduced significantly, and what we're actually seeing is an increase in natural gas use. Again, this is not talking about with the addition of renewable energies. This is just in the fossil fuel sector. What you see in North Carolina is that we are actively moving away from coal-fired power plants in lieu of natural gas. And we're actually not even generating as much energy from fossil fuels as we were in 2005. That's because we're picking it up quite a bit with our renewable or alternative energy sources. Oh, I forgot about this. In 2019, here is the kind of Duke Energy. So this is for North Carolina and the Southeast here. Duke Energy is essentially, now this is not just fossil fuel production in North Carolina. This is Duke Energy's mix of how they produce power in 2019. You'll notice that, right, coal is sitting over here. Natural gas is here. Nuclear energy is actually quite an abundant source of energy from Duke Power, with renewables at about 6%. They're actually, it's interesting, they've broken out hydropower as something else too, even though that would technically be a renewable. Now, look at the projection for what they're suggesting they want to have the mix to be in 2033. There's been some significant criticisms right now about this because folks are not They're not thinking that Duke Energy can actually make these changes. But notice what they're doing is they're going to continue to reduce our coal use. They are going to actually then increase natural gas, reducing nuclear a little bit, right, down to about 46%. And notice that hydropower doesn't really change much, but they are also then going to increase here the amount of renewables that they are using. So it's a lofty goal. I certainly hope that this can be done by the year 2033. But a lot of people right now are kind of questioning how this is going to happen, especially with the current infrastructure in the state. But you can also imagine, too, there will be lots of jobs associated with this, especially in the alternative energy sectors. So let's keep our fingers crossed that Duke Energy is able to meet these goals by 2033. Alternative energy really kind of didn't take hold until a couple of decades ago. And of course, it was met by significant resistance, right? Significant disapproval by the oil and the coal companies. And it makes sense as to why, right? You know, big oil, ExxonMobil, Chevron, Texaco, Anadarko, Oriental, all those big oil companies are making a ton of money by the country being totally dependent upon fossil fuel production. So of course it makes sense that, you know, these companies were very resistant at first to saying that they needed to explore alternative energies. But as we know, with climate change, with the shrinking reserves of coal, of natural gas, of petroleum, as those reserves are starting to get smaller and smaller, but the demand for energy is increasing as our population increases, we're going to have a little bit of a problem, right? We're going to end up with a shortage of energy. So in order to meet the demand, in order to effectively and efficiently abandon fossil fuel use, this idea of now turning to alternative energy resources is certainly timely and is going to be very important, say, in the next 10 to 20 years. So let's talk about our first type of alternative energy, and that's solar energy. So we have a couple of different types of ways that energy from the sun can generate essentially power. And it may surprise you a little bit when you think about this. So here's our energy from the sun, right? And believe it or not, energy from the sun powers all of these different types of alternative energies. Energy from the sun actually drives wind. Remember, we talked about how temperature differences in air masses can cause rising or sinking air masses, and that creates wind. Well, all of that has to do now with temperature change associated with sunlight. I'm going to show you in the next slide that there's two direct ways that the sun's energy can be converted into electricity. We're going to look at passive collectors and photovoltaics. But technically speaking, we're also going to talk about biomass burning, right? And of course, that's just plant material or urban waste. And all of that has been produced just by sunlight, right? Growing vegetation or what, you know, the food that we eat. And energy from the sun also can be essentially the main source for hydropower, right? Why water flows and whatever else. So we're going to talk about wind, hydro, biomass, and next I'm going to talk about these two types of collecting solar energy. But really, you know, the sun is our main source for a lot of these alternative energies. Did you know, happen to love this statistic here, just 10 weeks of energy from the sun is equivalent to the energy stored in all known oil, gas, and coal reserves on the planet. Just 10 weeks of solar energy. I mean, that should be pretty amazing to you. And that is essentially only 13% of the sun's actual energy reaches the earth. So imagine the possibilities if we were really able to harness the energy in our sun. We could certainly have a completely renewable source of energy that would potentially last the life of the planet if we could just harness it. And again, we're only getting 13% of the energy from the sun reaching the earth. Imagine what we could do if we could actually reach more of it. So definitely important to realize that the sun is the main source of energy for most of our renewable sources. So we're going to talk about two different types of solar power. The first one I want to talk about is a passive solar collector. And so literally, this is what it looks like, okay? It is a flat panel of glass. So the glass on top is clear, but underneath that piece of glass is a black background. And so you can imagine, right, here's the black background. You can see it here. Over top of that black background, though, is copper tubing. And so the copper tubing kind of winds through behind the glass like this. So the sun is attracted to the black background. It shines through the clear glass, and it heats water in the copper tubes. The sun's rays can heat the water to 100 to 200 degrees Fahrenheit. That is plenty warm for anything that you would need for your own home use. For example, right, your temperature in your shower, 107, 105, depends on how hot you like your water. But yeah, so that's plenty. And you can actually then pump in cold water here, right? The cold water would then go up to your passive solar collector. It would get warmed up by the sun, and then that hot water would come down and be stored into your hot water tank. So pretty neat way of just using passive solar collection, right? You're just literally using the sun's energy to heat up water in copper tubes. So that's a passive solar collector, but there's another way that we can use energy from the sun, and that's something called photovoltaics. Photo, right, meaning sun, and the volt part, you can actually remember, right, that means electricity, just like the volt in a battery. This is not a passive warming of water here. Instead, what you're actually doing is you're converting sunlight directly into electricity. So how do we do this? The photovoltaic cell is set up like this. You've got a glass plate on top, just similar to the one that we had in the passive solar collector. But beneath the glass, you've got metal strips that are essentially conductors. Photons from the sunlight knock off electricity from the metal atoms. And remember that if you're knocking off electrons from a metal atom, you're generating a flow of electrons, which is an electrical current. So the metal conducting strips essentially, right, just have a flow of electrons, and you then can create an electrical current. Very simple, right? Very easy. And so this is a little bit more expensive to create. These are kind of delicate panels, but it's a great way to, rather than just heating water, it's actually generating electricity that can be directly used for home or business use. So try to think about what are some of the benefits of solar power, right? What are some of the things that are good about this? Well, here's a couple that I came up with. It can be used in remote areas where they maybe can't afford fossil fuel energy, right? So there's pretty much sunlight is everywhere, right? And so it's relatively inexpensive to operate once it's installed, right? There is a pretty high cost to actually install this stuff. But once those solar panels are installed, it's relatively inexpensive to just kind of let everything run. It's environmentally safe, and by this I mean that there's no waste production, right? You don't give off any gases, you're not giving off any toxic material. So environmentally, once the panels are installed, they are pretty passive, right? There's nothing that you have to now actively do to keep them up, and it's not a constant concern for the natural environment. We mentioned already, right, that this is usable worldwide, whether it be in urban areas or extremely rural areas, but pretty much anywhere where sunlight is hit. And depending upon where you are and how much of it is being used, it is certainly developing into a multi-gigawatt per year product. So it is generating quite a bit more and more energy locally as well as globally. So it's turning into kind of a big source for renewable energy around the planet. In fact, in many developing countries, what they're actually doing is taking the concept of kind of a passive solar collector, and they're actually using it to just kind of make light bulbs, just using a 2-liter soda bottle filled with water and a little bit of, I don't know, bleach or something like that to inhibit algae growth. All you have to do is essentially take a 2-liter soda bottle, put a little bit of bleach in it, and then fill it with water. And then what you do is you cut a hole in the roof of your house and you slip the 2-liter bottle into that hole. So now the top of the 2-liter bottle, right, there's the cap, would be sitting above the roof of your house, and the bottom of the bottle is now sticking down into your house. The top part up here is collecting sunlight, and the sunlight is then transmitted into your house just through the water in the water bottle. This is pretty neat. So placing it through the hole in the roof can give you about a 50-watt bulb energy production, and it can last up to 5 years. And really the only thing that happens there is that the plastic starts to deteriorate, or you start to get algae growing in the bottle, and you can just replace it and essentially now have a very renewable light source, right? A little light bulb source. There are some drawbacks, of course, to solar energy, right? Since sunlight isn't targeted, right? Sunlight bathes the entire planet. It doesn't come in like these kind of targeted channels. Since sunlight is relatively dispersed, in order to collect solar energy, we need a large amount of land covered with these photovoltaic cells. Now what we can do, and I have to tell you guys, plenty of other countries are way ahead of us in doing this. We can actually start placing cells on existing structures, right? Buildings. Some people are putting this on roadways. When I flew into, I'm trying to think, I think it was Amsterdam first and then Edinburgh, Scotland. Flying into those cities, seeing what the UK has done, almost every building in Amsterdam and almost every building in Edinburgh, it's a pre-existing structure, it's already there, but the roofs, where nobody sees it except an airplane coming in, the roofs are covered in solar panels. So they're not using big, broad, open fields and making them into solar fields. They're using pre-existing structures and covering them with solar panels. It's very effective. It generates quite a bit of energy for the city, and it's already not taking any sort of free space or free land. It's using the buildings that are already there. Producing the actual cells can be expensive, but the costs are definitely coming down. I noticed over the last couple of years, I've been looking at maybe installing some solar panels on our house here. The costs are definitely coming down. So as the technology is getting better, we're noticing that it's going to become more and more affordable. Initially, solar panels were pretty low efficiency. And again, I'll update that. That's definitely getting a lot better now too. And so these two are kind of no longer becoming as big of a drawback as they used to be. Prices are coming down and the efficiency is certainly getting better. If we look at now too, I remember that I don't know that these drawings don't go away. Sorry about that. Here we go. If we look at now too, scheduled, this was from 2016, but essentially here, the amount of solar energy, right, the amount of gigawatt production that we were going to be producing in 2016 was certainly increasing, especially when it was talking about with respect to a lot of the other energy resources like natural gas, wind, and nuclear, and hydro. So the idea here of increasing the amount of solar infrastructure that we have in the U.S. definitely is a big push that we're seeing in recent years. Here's a graphic that I really want to focus on too, as we're talking about the idea of renewable energies. Let me just show you really quickly. I'm going to split this graphic kind of down the middle like this. This is, in 2019, the proposed additions to the energy infrastructure for the U.S. The circles are related, the size of the circle is related to how much energy is going to be produced, right, in gigawatts. But the color of the circle is showing you what type of energy it is. Notice that these are the proposed additions in 2019, and that many of them are wind, solar, and natural gas. In 2019, the retirements, right? This is the proposed retirements. The places that are going to be closed are mainly, notice over here now, right? 3 Mile Island. These are nuclear plants that they're going to be closing, coal plants that are going to be closing, and natural gas plants that are going to be closing. So you notice that there's certainly a push, even across the country, to start to get rid of fossil fuels and nuclear energy, and the reason that they're doing that is to replace them with renewables, right? Solar, wind, and then cleaner energy like natural gas. All right, one of the things that we can use in certain regions is geothermal energy. Geothermal, right? Literally, we're just talking about geo, right? That means earth, and thermal meaning temperature. So we know that as we go into the planet, temperatures get warmer and warmer. So if we can actually use that temperature as we go into the planet to either heat water or cool water, even in the summer times, that's a very natural source of energy, and it is certainly renewable. If you've ever been to Yellowstone National Park, you might have seen geothermal energy firsthand, right? That's what causes things like this, like geysers. Oops, geysers here like this. Or Iceland or something like that. New Zealand, these are all places that have lots of geothermal energy very close to the surface, and they've been very effective at using that. So what is geothermal energy? It is literally using the heat, right? The heat from the interior parts of the planet to generate electricity or heat, right? Either in your home or in your business, or essentially right in your private sector. So the idea behind this is that what you're going to do is use the principle that as you go deeper into the earth, right, temperatures get warmer. So it's cool at the Earth's surface and warmer at depth. The idea here is that you're going to place pipes into the ground. And what you're going to do, notice that the input into all of these pipes is the blue water, right? We're going to take cool water and we're going to pipe it down into the ground. By doing this, you are either going to just pipe that cool water down into the subsurface where it's going to warm up, and then you'll bring it back up to the surface. Or if you've got kind of geothermal ponds or lakes or springs or something like that, you can pump that water directly into the pond or the lake and it gets heated up, and then you pump it back into your house or your building. So you're just taking your cool water that you have in the house, right, coming directly from your faucets or your pipes. You're pumping it down into the ground or into a geothermal heat source, and then you bring it back up to your home. That water is being passively heated just by the earth around it, and so you don't need to use any sort of fuel source to heat up the water for your home or business. We know that the Earth's interior is hot. In fact, we even have a relatively consistent way of calculating it, that for every kilometer down in the planet you go, the temperature increases by about 25 degrees C. There's a couple of places, right, where things hiccup a little bit, but we call this the geothermal gradient, right? Remember, gradient is just like a slope. So it's the change in temperature as you go deeper into the planet. And what you'll notice here is that this is showing you temperature and this is showing you depth. So as you go deeper into the planet, right, the temperature increases at a rate of about 25 degrees C per 1 kilometer. Now look, we don't really even have to go all the way down to the mantle or the core or whatever else like that. I mean, having temperatures that are at 5,000 degrees Kelvin, that's a little excessive, right? We don't need that to warm a house. But even notice that at the crust, right, we're actually getting up into significant, 200 to 300 degrees Kelvin. That's plenty of energy to heat whatever we might need for our home or business. Geothermal energy around the U.S. has some challenges, right? Because not all places in the U.S. or in the world are going to have hot geothermal energy close enough to the Earth's surface that we can harness it. If we look at the map on the upper left here, this is showing you the temperature gradient, right, at a depth of 6 kilometers beneath the Earth's surface. And you'll notice that some places are relatively cool, right? So like places down in here, relatively cool, right? Not a whole lot in terms of temperatures there that we could use. But as the temperatures get up into the oranges and into the reds, we certainly now have the potential for, home use or industrial use. So notice out here, this whole stuff right in here, this is where we have a really high potential for using geothermal energy, at least in the US. Might make sense too, right? Yellowstone hotspot lives kind of right in here. This is actually an old rift zone, so there's a really thin part of the crust right there. So lots of reasons why there are really hot temperatures very close to the Earth's surface, at least in the western part of the US. If we look at the global map, right, that's what's being shown down here, the global map shows that these are the areas, right, where there's lots of potential for geothermal energy, even here along the mid-ocean ridge and out in Hawaii. Now, if you look at this map, it should be relatively similar to a map you've seen before. So why are there lots of areas that are really warm geothermal regions in these locations? What is this red line mapping? If you said plate boundaries, you are right, right? Plate boundaries. Remember, this is the subduction zone, right? This is the ring of fire over here in the Pacific. Hawaii is sitting on a hot spot. This is actually tracking the Mid-Atlantic Ridge, right? The Mid-Atlantic Ridge is there. And there's also a plate boundary cutting right through here, right? This is the East African Rift right through here in East Africa. And there's an old plate boundary right here where Africa is moving north and crushing into Europe. So along plate boundaries, there's lots of places where they can use geothermal energy because at those plate boundaries, usually crust is relatively thin and we've got really warm temperatures close to the Earth's surface. So how can we use it? We already talked about this place at this situation at the top, right? Where you can actually kind of in the, notice that here, this is winter, right? So in the winter, you can pump cold water down into the subsurface. And because it stays warm, right, at the beneath your house, you can kind of just let the water warm up at depth and then bring it back into your house by a heat pump. What's interesting too is that the temperature beneath your house in the soil probably stays pretty constant throughout the year, right? Just like a cave constantly stays at about 55 degrees, the bottom temperature of the soil might stay about 55 to 60 degrees. So what will happen then too is that in the summertime, notice that now over here we're in the summer, if you've got hot water, right, but you want to cool your house, if your water is hot, you can actually pump it down into the ground, allow the heat to kind of dissipate down here. The water will cool down because the soil down here stays at a constant temperature. And now you can pump that cool water up back into your house, use a heat exchanger, and actually create a air conditioning system. So these are how heat pumps are working. So the pump cooling water down into the ground, it can either get heated and then you can kind of pump it back up, or you can pump warm water down in the summers and it'll actually get cooled off a little bit and you can bring it back to your house. We can also do this on a larger, not just a household scale. We can do this on a geothermal power plant scale. What we're doing essentially now is that in places that have a lot of water, groundwater at depth, and that water is being heated by the geothermal energy of the planet, we can pump that hot water out and flash it to steam, and that steam can actually then be used to turn a turbine, and that turbine, of course, produces electricity that you can then pump out into the grid. So you can create energy by pumping out the hot geothermal water, and then the water that's now cooled, right, you can pump it into a cooling tower, you can put it back down into the ground, let it get warmed up again by the geothermal energy, and then you just pump it right back in. So it's a nice kind of circular energy circuit, but again, nothing is damaged, nothing is destroyed. You literally collect the water after you're done, you pump it back down into the ground, and it gets heated again by the temperature in the earth. So nice, clean way of generating electricity. What's the environmental impact of geothermal energy? Well, it's relatively minor, to be quite honest with you. Once the actual power plant is built, so you notice that it actually does have it has a significant footprint on the ground surface. But once the actual plant is built, you're not burning any fuel, right? You're literally just giving off. This is just excess steam right here. This is just water vapor. So this is not smoke. This is just water vapor being given off. And so it's just, that the plant essentially has too much steam to deal with the amount of steam needed to turn their turbines to create electricity. So it's just giving off the excess. But really, there's no waste other than water vapor being produced here. So relatively clean energy using geothermal heat. And some places have done an incredible job of using geothermal energy. This is Iceland, okay? And this is a picture of Iceland in 1932. Iceland is a very small country, right? They were burning tons and tons of fossil fuels. So you can see all the smog, right, that was sitting on top of the capital city of Reykjavik in 1932. Well, Iceland kind of made a real big push because Iceland sits on the mid-ocean ridge, right, in the North Atlantic. They made a push to get away from fossil fuels and to start really focusing on using geothermal energy. Here is Reykjavik today. 95% of the buildings in Reykjavik, Iceland now use geothermal energy. And almost 100% of the electricity produced in Iceland is from renewable resources. So they are really doing an incredible job of harnessing what they have locally: sunlight, geothermal energy, wind power, and hydropower. And they're producing almost all of their energy from renewable resources. And even just in the last, 100 years or so or less, right, they are really seeing a huge improvement into the environment. So the benefits of geothermal power, right, you can think about a lot of them here. Definitely clean, safe energy, right? It doesn't use a whole lot of land space. It's certainly renewable, and it's definitely sustainable, right? That means that it'll actually sustain into the future, right? We can actually continue to have geothermal energy into the future, even if we use it now. It generates continuous power, right? Essentially, we're not going to have pockets of time where the subsurface of the Earth isn't warm. It's always going to be warm, so we'll have a reliable power source. It conserves fossil fuels because we're not using those. We don't need a fuel source to keep that geothermal power going. We don't have to import, right, anything else. We don't have to import things like coal or gas or oil or anything like that. It benefits the local economy because you're building and creating jobs. It can certainly be used at remote sites. We're seeing that in all sorts of places of Iceland. And really, there's no waste production, right? You're not producing aerosols. And the gases that are emitted essentially are clean gases, mainly in the sense of water vapor. Now, with any sort of energy production, right, we are going to have a couple of negatives. So the one thing that is kind of a negative, right, I wrote easy question mark on the environment. We do at geothermal power plants produce some really hot wastewater, right? There is some wastewater that is produced. It's salty, usually because it's coming from deep inside the earth, and it has lots of dissolved minerals in it. So what do we do with that hot wastewater, right? Once we take that water and we turn our turbines with it, the water isn't just, room temperature or surface temperature. It's still relatively hot. And because it's saline and has lots of minerals in it, what do we do with it? Well, that's a problem, right? A lot of times we'll put it in storage tanks. A lot of times we actually then pump it back down into the subsurface, right? We inject those those fluids down into the subsurface to kind of recycle those. But that pumping can actually create earthquakes. They're relatively small, but it can certainly start to kind of trigger land movements. As with any sort of pumping, right, if we pump water out of the ground, we do increase the risk of subsidence, right? So even if you pull hot water out of the subsurface to run your turbines, of course, pulling that water out can create a big risk of land collapse. And of course, too, if you don't do it right, you certainly could disrupt the natural groundwater system. And we do know all about that by pumping and creating things like cones of depression, changing the direction of groundwater flow, and potentially drawing in contaminants. So these are all things that certainly need to be considered, even though it seems like the pros are certainly numerous for using geothermal energy. Remember too, though, that, very few cities lie very close to geothermal areas, right? This is, Reykjavik is very lucky in that it sits right on that mid-ocean ridge. But lots of other cities, right, most of the continental interiors don't lie anywhere near a geothermal energy source. So it's kind of challenging. that geothermal areas are pretty localized, right? Definitely a localized energy source. Right now, at least, too, geothermal energy provides just a small proportion of the energy needs that a city or a country actually needs. Don't forget, too, that if you pump out the groundwater too fast and you don't replenish it, then the cycle stops, and then we've got a big problem, right? If you don't have any water pumping back into the system to get hot, then essentially you have shut down your entire energy source. Also, currently, it's relatively expensive, and again, we're getting better with this, but right now it is expensive to input geothermal energy, at least into a home or business. I think, and I don't think Brian Zimmer would be too upset if I mentioned this, to put it into a modest house, it costs something on the order of $20,000, $16,000 or $20,000, I think, to put in a geothermal heating system. Your normal, heat pump system or whatever else, or normal HVAC, if you were using oil or whatnot, could be on the order of, $8,000 to $10,000 for a relatively modest house. So it certainly has a higher cost. So it certainly is expensive, but the potential, of course, is what everybody is really focusing on right now. The potential of reducing the hydrocarbon use, right? 1% of the energy produced in a 10-kilometer region using hydrothermal power is equal to about 500 times the amount of energy in that same space that could be produced by hydrocarbons. So I think once the costs come down and we get more efficient at this is certainly going to be a important renewable energy, of course, associated with just places where you can actually reach that heat in the subsurface. Right now, U.S. geothermal power, right, relatively small, showing that it's only about 0.5% so far in the U.S. total energy production. But like I said earlier, it's certainly getting better. And where are we seeing a lot of geothermal power? Of course, it is mostly in the western part of the U.S. And you remember we showed that map as to why it's in the western part of the U.S. Certainly important because you need to have the energy very close to the surface. It needs to be hot. So they're showing here the kind of currently installed and then the planned, right, geothermal energy in these western states. Now we do have a couple of small geothermal sites here in North Carolina and in South Carolina and in Tennessee. But again, because we don't really have a whole lot of geothermal power close to the surface, of course, it's certainly not going to be feasible for us to do that anywhere in this area. Breakdown of geothermal energy production, right? Of course, across the world, who's doing really well at it, right? Who's producing a lot of energy from geothermal? The U.S. is actually doing pretty well. Notice that number 2, you may not have expected this, is the Philippines. Number 3, Mexico, doing really, really well. And given how small it is, notice that Iceland is right here and New Zealand are right here. These are really, really small countries, especially when given, things like the U.S. and Mexico. But because they are sitting right on these geothermal hotspots, it's really amazing that almost 100% of the energy, right, produced in Iceland is coming from geothermal or renewables. Same thing with New Zealand. So some countries doing really well with the amount of geothermal energy production across the world. Let's talk a little bit about hydropower too. This is a little bit outdated, right? Remember, we told this is up to about 11% now, but we're talking about kind of hydroelectric power. About 20% of the renewable energy resource, but it's less than 10% of electricity in the U.S. Again, getting better, but we can actually use the power of water just moving naturally throughout its watersheds to create either electricity or just to create mechanical power, right? Like moving a turbine or moving a water wheel. Certainly important because we can cut the import costs for fossil fuels, and generally speaking, the waste production of hydropower is extremely minimal. So what we're doing is essentially with hydropower, we're harnessing the power of water flowing downhill. If you put in a dam, right, so we're just going to put in a dam, you're going to essentially build up a huge package of water behind that dam. Now, essentially, you have water sitting at a high elevation. On the other side of the dam, right, the water is at a lower elevation. So essentially all we've done is we've created, right, hydraulic head, right? We've actually created essentially a change in the elevation between the water up here and the water down here. And so water, of course, wants to flow downhill. When you open the sluice gates of a dam, what happens is the water flows into the dam, flows downhill, and at the bottom of the dam, there is a huge turbine. The water flowing through the paddles on that turbine creates electricity, and then that electricity can then be pumped out into the electrical grid. The water then flows through the rest of the turbine and out into the downstream outlet, and essentially you don't have any net loss of water. It just keeps moving along its path to the ocean. A couple of negative things, of course, about building dams, right? You're going to get a lot of sediment buildup behind that dam. There's going to be problems, of course, with fish that want to get from one part of the stream to the other. But let's talk about those in a second after we kind of talk about the ways we can harness the hydropower. Now, you can also use the power of water moving if we actually harness tides. So this is tides coming in and going out, and places like the Netherlands and the UK are doing very, very well with this. Also places in Canada. When the tide comes in, right, the amount of energy coming in, what you can do is now you can actually force the tidal energy to go through a relatively small channel and put a turbine in that channel. So as the water is rushing in during the incoming tide, you turn the turbine here and you generate electricity. Same thing works when the tide actually comes back out. You funnel it through a very narrow area. You turn a turbine, and that turbine essentially then generates more electricity, and you send it out into the grid. So this happens, right? You know, incoming tides twice a day, outgoing tides twice a day. So you can actually create quite a bit of electricity just by the natural movement of water. And think about the implications of places like this, the Bay of Fundy in Canada, where tidal changes are on the order of 50 feet, right? The tidal surge is on the order of 30 to 50 feet. That's a lot of water rushing in and out several times a day. So harnessing that's certainly important for places in coastal regions. Relatively clean power, right? The impacts of hydropower. Relatively clean because if you think about it, here's a good example. This is the dam here. Notice how high the water is on this side and then how low the water level is on this side. This is the water coming out of open sluice gates. So relatively clean power because look, what are we actually producing as waste? Pretty much nothing, right? No energy, no gas emissions, no nothing like that. We're not burning any fuels, we're not producing any pollution, and we essentially aren't producing any waste, at least from the energy production itself. So it's, you know, a pretty clean energy source and certainly renewable, right? As long as the water keeps flowing. However, we do have problems. By the way, this is the Hoover Dam, right? This is a picture I took from a helicopter over the Hoover Dam. Pretty cool. This is the Hoover Dam. There is some problems associated with hydropower, and you can imagine, right, when you build a massive dam structure like this, you are essentially blocking the natural flow of water down a river. What can happen? Okay, what you can actually do is you can trap sediment behind the dam, and that can actually load the surface behind the dam. It can block fish migration, right? So if the fish are on a migration path and trying to move down the river, oftentimes what happens is that they can't get through the dam, disrupting spawning or breeding or anything like that. A lot of times too, stagnant water behind a dam can actually start to collect nitrogen. You can actually get oxygen depletion that can cause fish kills. Think about too, when you put in the dam, right? When you actually put in the dam and then you flood the river behind the dam, this river, right, used to just be this little tiny narrow thing right here, but now we've flooded this entire valley. That's going to displace all the people and the animals that used to live in those valleys. And then of course too, you can think of what happens when and if the dam breaks, right? And all that water now rushes down this channel here. Another thing that's associated with building dams is that if you build a dam like the one shown here and you pond up all this water back on this side here, this becomes extremely heavy. So all that water sitting on the land surface uphill from the dam actually can trigger earthquakes underneath the flooded valley here. And if the earthquakes are big enough, the dam can break, and then you have a bigger problem on your hands. Here's the U.S. National Hydropower map, essentially showing the plant types, right? The types and sizes of the plants that are producing hydropower. And then the color of the dots shows essentially who owns it, whether it's the U.S. Army Corps of Engineers, the Tennessee Valley Authority, or whatever else. But essentially, of course, where there are big watersheds and big rivers, we're certainly going to have a lot of hydropower potential. So lots of stuff over here, of course, in the Appalachians, in the Mississippi River watershed right over here. And don't forget, right, you've got the Rocky Mountains. And so we're also then going to have lots of rivers draining off the Rockies coming this way. So lots of places over here certainly going to be using hydropower. So we're doing pretty well with this. If you want to take a break, this would be a great place to do it, right? Because when you take a break, go take a breather, run around the yard for a little while, and then come back. We'll talk about wind power and nuclear energy. Okay, we already talked a little bit about wind power and essentially what causes the wind to blow. And remember, this is just essentially temperature caused by energy from the sun, right? So during the day, the land warms up, and so hot things rise. So air rises over the land and it sinks down over the oceans because essentially the oceans remain cool. So you can create wind that way from a low pressure system to a high pressure system here. In some coastal regions too, the wind direction changes at night because now what you've got is the water is warmer than the land, and so air rises over the warm water and actually sinks over the land surface over here. And so now here is where you have low pressure and here is where you have high pressure. So literally you can create in coastlines wind directional changes just by day and night temperature change. Wind power, of course, is becoming a huge thing in many other countries. Here's an offshore wind farm in Sweden. Believe it or not, even in places that you don't think would have huge wind fields. Here's the Lake Turkana Wind Project in Kenya. Absolutely amazing what's being done with some of this. And in some regions, of course, right, you're using land surface for your windmills. But in places where there are coastal regions, Sweden, the Netherlands, oh gosh, the UK has tons of these. What they're doing is they're putting their windmills actually out into the ocean so that you're not using valuable real estate, but instead you're generating your electricity offshore and then just kind of piping the electricity back on land. So we're going to move a turbine just by creating wind, and that movement of that windmill, that turbine in the windmill, will create electricity. We're actually seeing that throughout the U.S., right? We're getting better and better with the amount of windmills that we're putting in. Notice where a lot of them are actually being put in too. Tons and tons and tons of them are being put in here in the Midwest. Of course, makes sense. This is Tornado Alley where we get lots of wind, but also the upper Midwest over here where we are generating lots of temperature changes in the middle part of the country, and therefore makes sense because we're creating lots of wind movement. So wind is, of course, widespread, kind of happens everywhere, right? It is abundant. It is inexhaustible, right? We just make more temperature change from the sun and we create more wind. Once we put up the windmills, to generate the energy is relatively inexpensive. And once again, we're not burning any fuels or giving off any sort of emissions. So wind power is relatively clean. There are disadvantages to wind power though, and a lot of people actually use the NIMBY idea here. This is the N-I-M-B-Y, right? NIMBY, not in my backyard. Lots of people like the idea of renewable energy or using alternative energy sources. However, they don't necessarily want it in their backyard. The reason that a lot of people don't want windmills nearby is, of course, they do kill birds. This is a reality, right? This happened with the Boone windmill, not the one that's at on App's campus right now. There used to be a large windmill at the top of Howard's Knob. And believe it or not, Boone residents were actually complaining that it was pretty loud. They said it actually just had this constant whirring sound that was kind of bothersome. Interestingly enough, I kind of did some research on how loud a wind turbine is. And if you're literally right up against the windmill, it's about the same loudness as a lawnmower. But look, if you go just 100 to 300 to 500 meters away, half a kilometer, 500 meters away, it's actually now the sound has actually dropped to below the sound that your refrigerator in your kitchen is making. So I think, the windmill that they had in Boone was, several decades ago. And I think right now, current windmills are much, much quieter. And so the noise essentially has been significantly decreased. And notice what it says here too, wind turbines in residential areas are placed no closer than 300 meters from the nearest house. So look, you're actually between the noise of a window air conditioner and your refrigerator. So certainly shouldn't be an issue with it being loud anymore. One thing though is that they do take up a large amount of land space because of course putting in one windmill is great, but a lot of times you see these put up in, huge fields. So generating quite a bit of energy takes a large amount of space. And of course, a lot of people just don't like the way that they look, right? The idea of not in my backyard, they don't want to actually see the windmill in their area. I kind of like it. Every morning when I drive into Boone for class or whatever, I see the windmill that is up at the top of Bodenheimer Drive. And that kind of makes me feel pretty good about the fact that, we are committed, at least in somewhat, to helping produce energy in Boone from some sort of renewable clean energy. Who's doing it and who's doing a good job of it? Now, remember, the total amount of energy produced in the U.S. by wind is only on the order of, 6 to 7%. But of that 6 to 7% of energy that is being produced by wind, Texas, believe it or not, is actually doing one of the best jobs. And they actually were highlighted recently as doing some of the best work in terms of putting in new wind fields and producing a lot of energy by wind. But also notice the Dakotas, Kansas and Oklahoma, Iowa, and up here even, believe it or not, in Maine, right? Actually producing a lot of energy by wind. So should make sense that there's a lot being generated here in the Midwest, right? This is all the winds kind of rushing off the Rocky Mountains heading this way. And so doing pretty well, at least in the middle part of the country, generating a lot of their electricity by wind energy. I always had a curiosity about Boone's windmill, and I'm not talking about the one that they took down on Howard's Knob. Now, this is the one I'm talking about at the top of Bodenheimer. It was installed in 2009, and what happened is that the university asked the student body, would they be willing to agree to a modest increase in tuition if that increase in the tuition was used to build a windmill? I'm talking literally, it was like, $10, $15 per student. I forget what it was, but it was not a lot that they had to have buy-in from the students. And the students agreed, absolutely. And what they installed was a 100 kilowatt community scale wind turbine. And here it is, okay? The cost to put it in was about $500,000 for one windmill. So that kind of tells you a little bit about how expensive it is to put these things in. It has the potential to generate 145,000 kilowatt hours. That is equivalent to about enough energy to power 10 to 15 homes for a year. Now let that sink in. $500,000 to produce energy to power 10 to 15 homes for 1 year. So that's a huge cost for only powering 10 to 15 homes for a year. The windmill that we actually have in Boone is it looks very industrial, but it's actually not one of the most efficient ones that's out there. So I do want you to realize that, yeah, Boone is generating some energy from its windmill. It's great. Whatever it's not using, it's putting back into the grid, which is awesome. But some windmills can be extremely expensive and aren't very efficient. We're getting better again with the technology here. So I think over time we have the potential, of course, to add more at lower cost and then create a larger proportion of Boone's energy from wind energy. We also want to talk a little bit about biofuels, right? What the heck are biofuels? I like to call these the unfossil fuels, right? This is literally things that are made by burning or using current vegetation, right? They haven't been fossilized yet, so they are unfossil fuels. So we can use things that are fermented from sugar or starch crops, right? Things that we can produce ethanol from corn. We can create methanol from corn, and these are kind of cool because methanol and ethanol can be used to replace gasoline. You can also create certain types of vegetable oils, right, from the transesterification, think of like literally esters or trans fats from some of the vegetable oils that are made, and you can create biodiesel. So that can be a diesel replacer right here. You also can actually then, just by burning or producing things like algae or other types of vegetation products, you can actually create methane, right? Just by the decomposition of organics, you can actually produce methane gas. We can use that methane gas to, it's flammable, we can burn it, you can be used for heating. You can create hydrogen, which can be used in fuel cells. You can actually create DME, which is also then produced from the dehydration of methanol and can again be used as a fuel source. So there's lots of things that can either be used as replacers or can be similar to petroleum fuels that can just come from either the actual organic material or the sugars and the esters in that organic material, or from the burning of that organic material to create things like gases that we can then use. So pretty neat stuff. We're using organic matter such as plants and animal waste to produce energy. Several other countries are doing a great job at this. Germany, believe it or not, Germany has a huge biofuels program, and they're actually using a lot of methane production and just burning of biomass to actually offset about 10% of their energy production within the entire country. Biofuels right now only make up about 5% of U.S. energy consumption, but of the actual proportion of renewable energies, right, we are getting much, much better in terms of the amount of biofuel production that we are getting from biomass, right? So look at corn ethanol, right? That's the kind of magenta colors down here. Other types of biodiesels and biofuels are the other things that are coming up in here. But we are definitely noticing that over time, right, here's 2013, here's getting closer to today, we are certainly seeing an uptick in the production of biofuels, making more of a dent in the amount of energy that we are producing that's coming from something that's renewable, right? Something that we can continuously grow, like plants, algae, and corn. A lot of farmers in the U.S., especially in the breadbasket, are growing a lot of corn. Corn is actually in a lot more demand now than it ever was. Not only do we use it for feeding livestock, and that's something that we've been doing for years, is feeding livestock in cattle feedlots, especially that corn. But what you notice is that if you look at the amount of corn supply in 2004, 2005 to 2015 and 2016, the amount of corn going to feedlots is actually decreasing, and a lot more of it is now going towards biofuel production. And you'll notice too that a lot of that has to do with the production of ethanol. We're putting ethanol as an additive now into a lot of our gasolines, right? And there may be some things that you've heard about ethanol in your gasoline that may be true and may be actually not true. So I kind of want to dispel some of the myths about that. When I was first doing some research about this, a lot of people were saying, "Oh gosh, you shouldn't be putting ethanol into gasoline. It actually takes more energy to make ethanol than it does than the fuel actually would produce once you make it." That is actually false. It doesn't take more energy to make the ethanol than the ethanol would produce when you put it in an engine. So that's actually false. A lot of people also were saying too, these are people who kind of were against the idea of biofuel production, that ethanol crops and the production of those, corn crops and whatever else emit more greenhouse gases than just burning straight gasoline. This is also false. So it's actually, a lot of people were saying that, well, it actually even takes 1 liter of gasoline to make 1 liter of ethanol. That is 100% false. So the other folks were saying too that ethanol requires too much water to produce, so that you're actually using too much water as a resource to make the ethanol. That's also false too. One thing that is true though about using ethanol is you will actually see a slightly lower gas mileage using straight ethanol than using either ethanol and gasoline, or of course then just straight gasoline. But what's the benefit about this is that ethanol burns a little bit cleaner than the gasoline, and it also is a renewable energy source than the fossil fuel gasoline. So using the ethanol as an additive means that you don't have to use as much fossil fuel gasoline, and you still get your car to move and whatever else. So good things and bad things, of course, associated with biofuels, specifically ethanol. So let's now talk about nuclear energy. The last thing I want to talk about here is nuclear energy. And remember, we talked about in the beginning of this discussion, we said, okay, notice that in 2019, North Carolina, Duke Energy is looking at about 52% nuclear, but by the year 2033, they're looking to reduce that a little bit. And again, if we look at how the U.S. is planning, right, the retirements, they're actually thinking of retiring quite a few very large nuclear power plants, specifically 3 Mile Island in Pennsylvania and the Pilgrim Power Plant, which is actually in Massachusetts. So while nuclear energy is still a good almost half of the energy that is produced across the U.S. and also in North Carolina, we are seeing that there is hopefully going to be a decrease in the coming years in the amount of nuclear energy, and hopefully more renewable and cleaner types of energy. So we'll talk about nuclear energy, what it is, and then of course what the challenges are as well. How do we make nuclear energy? Okay, we're going to use the idea here of fission, nuclear fission. Fission is the process by which you're going to break an atom apart. Okay, so you have an atom right here, and this is the nucleus of the atom right here, and you're going to shoot a neutron at that particle, okay, at that atom. What will happen is that the actual nucleus of the atom will split, and as it splits into 2 fission products, the byproduct is energy. As that energy is produced in the form of another neutron that's given off will then hit another atom, which then causes it to split, giving off energy, and so on and so forth. So there's a chain reaction that goes here with the idea of nuclear or atomic fission. So a nuclear power plant uses uranium, right, atoms inside a reactor to create a process called nuclear fission. The energy that's given off from the fission creates heat. The heat turns water into steam, and that turns a turbine to create energy. So our little incident neutron, right, our little guy right here, here's our troublemaker. He comes in and he bombards the uranium atom. This is the uranium atom right here. He splits it into 2, right? And in that process gives off krypton and barium here, and then also produces more incident neutrons. This is the part that's interesting, because now these little troublemakers can go off and hit other uranium atoms, splitting them and making more incident neutrons that can then go off and make more trouble. So each time one of these little incident neutrons hits a uranium atom and causes it to split, energy is given off. Okay, and it's the energy that we want given off in the fission process that creates heat that we can use to make energy. So here, 1 gallon of nuclear fuel is equal to the energy in 2.7 barrels of oil. So we actually get more bang for our buck if we use nuclear fuel with respect to fossil fuels, specifically crude oil. This is kind of a perpetuating system because as we continuously use the fission reaction to create more incident neutrons, right, we set up that chain reaction, so we're constantly generating more and more energy as long as we have uranium atoms for those incident neutrons to bombard. So how does a nuclear reactor work? All right, first and foremost, we're going to start over here. Remember that uranium is a radioactive atom. So we have uranium in the reactor core here, and it's got to be within some sort of a confinement structure, right? It's got to be contained so that the radioactivity doesn't get out into the environment. But we'll put the uranium in the reactor core here, and we will allow now those incident neutrons to start to bombard the uranium atoms, giving off energy. And what happens then is that water that is around the reactor core gets heated up by that energy release and put into a steam generator. When we pump out and create that steam, we pump it into a turbine room, we turn that turbine, that creates electricity, which we can then send out into the grid. The water that is now, that has been used already to generate the steam can now be pumped back into the reactor core to be reheated and start the process over again. Or we can also then continuously use cool water from surface water. We can bring cool water here into this system, pump it now in, and have another, if we need more cool water coming in to be heated up by the steam generator, we can bring in more cool water there, then be generated by the steam that is generated from the heat here, and keep the system going. The radioactive atoms that we're using, remember, are uranium, okay? And they are packed into a very small space in the reactor core. The chain reaction that happens, right, where the incident neutrons are now hitting the uranium, so here's my little neutron hitting the uranium, we're going to make more neutrons while giving off electricity. That reaction happens really, really quickly. So what they do in a nuclear reactor is they install in the reactor core things called control rods. Those control rods are put in between. Notice here's the control rods and here's the fuel rods. In the reactor core, these fuel rods are made of uranium. Okay, so that's the actual fuel that we're going to bombard with those neutrons to make energy. But in between those fuel rods, we're actually using things called control rods. The control rods kind of act to slow down the fission reactions so that essentially we don't have a chain reaction going too fast to where too much energy or too much heat is produced. If the control rods fail and the chain reaction isn't slowed down, what can happen is you can get a nuclear reactor meltdown. What will happen is the chain reaction will happen so quickly that too much energy is produced, too much heat is produced, and literally the reactor core will begin to kind of implode and melt down on itself. Super important that we don't let that happen, right? And so keeping up with these control rods is certainly critical to the health of a nuclear reactor. The geology of uranium, right? What are we using? We are using uranium-235, which is essentially an isotope of uranium-238. So we have a good amount, right, of uranium-238 on the planet, but uranium-235 is the one that we need for our nuclear reactions, and only about 0.7% of all of our uranium on the planet is this uranium-235 that is fissionable. So it's actually, believe it or not, we have a lot of uranium-238, but the isotope of uranium that we need for nuclear energy is relatively low. So, of course, it means that when we mine uranium, it needs to be enriched significantly. Remember, we talked about those concentration factors of certain minerals, right? It has a very high concentration factor to get at that uranium-235 isotope that we can then use in our nuclear reactors. Uranium-235 has to be milled. We have to mine it out of the ground, right, and then crush it down in the milling process. It then has to be enriched significantly and then refined. And you remember we talked about this, right, in the mineral cycle. We said that you've got to find it first, right? You've got to do exploration. Then you've got to get it out of the ground. Then you have to kind of refine it by milling it, enriching it, and then kind of really isolating what you need. Then the uranium-235 is pressed into little fuel pellets, and those fuel pellets are put into the fuel rods that then go into the nuclear reactor. Here, once again, is just a little GIF kind of showing the idea that here's where the main action is happening. Here's where the heat is being produced. This is where the uranium fuel goes with the control rods. You then actually heat up water. The water pumps through a water tank. You create steam, turning the turbine, and then you get electricity heading out into your city this way. Where are the world's deposits of uranium? Believe it or not, there's a ton in Canada. So there's a lot of uranium production in Canada, Australia, Niger in Africa, and a couple of other places too, like Namibia, South Africa, and then only about 11% here is found in the U.S. So U.S. doesn't have a ton of it, but of the world's production, right, we're actually not doing too bad, about 1/10 of the cumulative world production of uranium. Canada almost at 1/3 of the world's production there, followed closely by Australia. With that nuclear energy, having that uranium, using that uranium-235 isotope, which remember is radioactive, means that once we use the uranium-235 pellets in the fuel rods, over time, right, we're going to deplete the amount of uranium in the fuel rod. So after about 1 to 3 years or so, the fuel rods are essentially used up. Now, it doesn't mean that there's no radioactivity left. It just means that there's not enough uranium-235 energy left in that fuel rod for it to be useful to produce steam and to produce electricity. So every 1 to 3 years or so, the fuel rods that have that uranium-235 in them have to be replaced. Here's the problem. The spent fuel rods are still radioactive. And they're still very, very hot, right? There are still reactions going on within those fuel rods. And so they are still hot. And so what do we do with them? We place them into cooling tanks, and the water that we pump into those cooling tanks helps to keep those fuel rods cool so that they don't go into chain reaction and meltdown. Once we cool down those spent fuel rods, we've used essentially up all the energy that the chain reaction has produced. Now we still have that cooled down spent fuel rod, but it is still radioactive. That radioactivity is producing things like krypton, strontium, cesium, and plutonium. These are still all radioactive elements, and we should wait at least 10 half-lives for these to break down into daughter products that are not harmful anymore. So uranium and, spent fuel rods from a nuclear power plant should essentially be sequestered for more than 250,000 years, even after they've been used. So where do we put this nuclear waste? We talked a little bit about this with Yucca Mountain when we talked about waste disposal. These are some pretty nasty things, right? Krypton, plutonium, and whatever. So we have got to find places to put this spent fuel and to keep it sequestered for about 250,000 to 500,000 years. We've talked about deep sea burying this stuff, right? And we even talked about too some of the ideas of, putting it into subduction zones and whatever else. Many people are currently leaving it at current storage sites. So they are actually storing nuclear waste at the sites of the nuclear power plants. So 3 Mile Island and other places like that. Years ago, lots of folks were suggesting we could actually drill and put the nuclear waste beneath polar ice sheets. Given our discussion yesterday about climate change, that may not be such a good idea anymore. It's very expensive and also, certainly very anthropocentric of us to think about this, but a lot of folks are suggesting we could load it up onto a rocket and shoot it into outer space. Kind of the out of sight, out of mind idea, but of course you can imagine the problems associated with now a rocket filled with nuclear radioactive material that is now somewhere floating out in space. What seems to be the most feasible is to now use deep underground geologic repositories, right? We talked about Yucca Mountain and how it was built to store the U.S. nuclear waste, but that we've actually already got enough nuclear waste now to fill Yucca Mountain, and it's actually never been used. So we are exploring, the government is exploring ways that we can find deep underground geologic repositories. And one of the things that is actually gaining a lot of traction is using salt deposits. There are huge salt deposits in the subsurface of the Earth's crust, and salt is crystalline, right? Salt as a crystalline mineral is relatively impermeable. So using kind of salt deposits to seal off and cap off nuclear waste is certainly gaining traction. Just remember, though, that if you do ever get groundwater leaking through salt, salt is also highly soluble. And so there is the worry, therefore, about salt being soluble and potentially, therefore, not being a great place to put nuclear waste. The risks and hazards of nuclear energy, of course, are very real. And I know you guys have all actually heard about this 2011, the Fukushima meltdown that happened in Japan. And again, like I mentioned too, check out the new, I think there's one on Netflix and then there was one on, I can't remember what other channel, but there were two recent, just a year or two ago, movies made about the Chernobyl disaster in Russia. These are incidents where there were meltdowns, there were problems with the control rods and keeping the temperature of the nuclear reactor under control, so that there was a radioactive meltdown of the reactor core, which of course then created huge radioactivity leaks, not only into the atmosphere, but then also into the Pacific Ocean, at least from the Fukushima meltdown, which then did make it across the Pacific over time and potentially impacted the coastlines of Canada and the US. Remember too that nuclear energy production does produce that huge radioactive waste problem, and there are tons of health concerns. Not with nuclear energy if it is done right, but of course the risk of meltdown or radioactivity leaks can certainly create huge health problems associated. With the Fukushima power plant, actually, this is where the actual Fukushima plant was located, right over here in Japan. And this is the spread of radiation in the Pacific associated with the meltdown of the Fukushima plant. So this is spread of the radiation into the Pacific Ocean basin from power plant number 3 from the Fukushima plant in March of 2012. Remember, I showed you on the previous slide, it actually happened in 2011. So it took some time, but essentially you can see, by the way, this is Hawaii over here, right? So this is definitely in the plume from the Fukushima power plant. And if we look here too, whoops, there we go. Here are radiation levels in the Fukushima prefecture. This is in Japan, right? The meltdown happened in 2011, and this is showing radiation up to 2016. You'll notice, of course, that the hotter the color, right, the more radiation was associated in that area. So you can see that here is the distribution of radiation in 2011, and even several years later, we still have extremely high levels, very close to the Fukushima plant here, showing some hazard associated still even 5 years after the initial meltdown. There's still problems even in Chernobyl, right? There's still radioactivity associated with the Chernobyl meltdown, and that happened in the 80s. So of course, right, nuclear power is certainly cleaner than fossil fuels, right? We don't produce CO2 or other greenhouse gas emissions. We don't have the acid rain potential. And essentially, we don't have a global warming issue. The only waste that is given off is water vapor. Again, water vapor is a relatively mild greenhouse gas, but we can actually then either recondense that and put it back into surface streams or whatever. The major problem, of course, with nuclear power, even though it is an alternative energy, the radioactive waste is a huge problem, right? All the challenges with what to do with that. But then also too, right, uranium-235 is a limited resource. So this is certainly an alternative energy to fossil fuels, but not necessarily renewable, right? It's a non-renewable because we do have limited amounts of the uranium isotope needed to then create that fission reaction. Well, guys, that's it for our lesson today. I hope you had a great semester. I know that this was challenging, especially with the online labs, but I really want to thank you guys for your flexibility and your ability to kind of work with me and each other on how to figure out how to do this in an online format. So I really do appreciate you guys. I hope you learned some fun stuff, and I hope we kind of touched on a topic that at least you had some interest in. So don't forget, right, your final exam is coming up, and if you have any questions before then, please don't hesitate to get in touch. And if I don't talk to you before the end of the semester, have a great rest of your summer, and thanks so much for taking my class. I really enjoyed having you guys.